Imagine, if you will, a tank. In your mind, you probably see a towering beast of steel, like an M1 Abrams or a German Tiger. You see a massive turret, a long gun barrel extending forward, and a crew of 3 or 4 men working in a cramped, noisy interior. Now, erase that image. Replace it with something that looks like it crawled out of a science fiction novel, or perhaps a flattened beetle made of armor plate. This machine stands only 1.74 meters tall. That's about 5 feet 8 inches, shorter than the average adult man. If you stood next to it, you could look over the roof without standing on your toes. Inside, there is no loader, no gunner, no radio operator. There are only 2 men, and they are not sitting in the hull. They are both squeezed into a flattened, pancake-like turret. But here is the truly strange part. The driver is also in the turret, but he isn't rotating with it. He sits in a separate, independently rotating capsule inside the main turret. When the gunner turns the turret to the right to fire, the driver's pod mechanically counter-rotates to the left, keeping him facing forward no matter where the gun is pointing. It is a turret within a turret, a dizzying feat of mechanical gymnastics. And the gun itself? It isn't a gun at all. It's a launcher for guided missiles capable of punching through 500 millimeters of solid steel armor from 4 kilometers away. The tank moves on a hydropneumatic suspension system that allows it to lower its belly to the ground, effectively kneeling to hide in the grass like a predator. This was not a concept drawing. It was not a prop from a movie. It was a real, functioning prototype built by the Soviet Union in the early 1960s. It was called Object 775, and for a brief moment in history, it looked like the future of warfare. Object 775 was not merely an experimental tank. It was an attempt to redefine what a tank fundamentally is. For 50 years, the recipe for a tank had been the same: big gun, heavy armor, tracks. This machine threw the recipe out the window. It asked a radical question. What if the gun is obsolete? What if the tank of tomorrow is not a brawler, but a missile-slinging sniper that is almost impossible to hit? The project ultimately failed. You won't find Object 775 in the history books of great battles. It never saw combat. But the reasons for its failure are far more interesting than the machine itself. They tell us a story about the limits of technology, the dangers of over-specialization, and the eternal struggle between revolutionary ideas and the messy reality of the battlefield. To understand why anyone would build such a strange machine, we have to look at the world of the early 1960s. This was the era of the missile revolution. In the United States and the Soviet Union, military planners were intoxicated by the promise of rocketry. Intercontinental ballistic missiles were reshaping the logic of nuclear deterrence, making long-range bombers seem vulnerable and slow. Surface-to-air missile systems were shooting down spy planes at altitudes that were once considered safe. And on the ground, the first generation of anti-tank guided missiles, ATGMs, was appearing. These wire-guided weapons could be fired by a single infantryman and destroy a heavy tank from thousands of yards away. There was a growing belief in military circles, a dangerous kind of technological optimism, that the old ways of war were dead. The mantra was simple: if it flies, a missile can shoot it down. If it crawls, a missile can blow it up. The era of dumb kinetic weapons, of shells and bullets, seemed to be ending. The era of the guided weapon had arrived. At the same time, traditional tank design was hitting a wall. The main battle tanks of the day, like the Soviet T-55 or the American M60, were becoming heavier and heavier. To defeat modern anti-tank weapons, they needed thicker armor. Thicker armor meant more weight. More weight meant bigger engines and worse fuel economy. The guns were also a problem. To penetrate the armor of the enemy, you needed a bigger gun. A bigger gun meant more recoil, which required a heavier turret and a larger chassis to absorb the shock. It was a vicious cycle of increasing size and cost. Logistics officers were terrified. How do you transport a 60-ton monster across a bridge that can only hold 40 tons? How do you fuel an army of gas-guzzling giants? The Soviet leadership, led by Nikita Khrushchev, a man famously obsessed with missiles, began to question the very future of the tank. Was the traditional tank a dinosaur? Had it reached its evolutionary dead end? This crisis of confidence led to a strategic leap. Instead of trying to squeeze a little more performance out of the old design, making the gun 5 bigger or the armor 10 thicker, Soviet engineers decided to try something completely different. They explored the idea of replacing the gun-based paradigm entirely. They imagined a vehicle that wasn't a tank in the traditional sense, but a mobile missile launcher with heavy armor, a missile tank. This was not evolution, it was disruption. It was an attempt to leapfrog the West, not by building a better tank, but by changing the rules of the game. Object 775 was the physical embodiment of this idea. It was designed to be small, agile, and lethal at ranges no conventional tank could match. It was supposed to be the weapon that made the heavy gun tank obsolete. But, as we will see, innovation is rarely a straight line. Sometimes, when you leap into the future, you land in a trap of your own making. The engineers behind Object 775 were not just building a new tank. They were building a new doctrine. They envisioned a battlefield dominated by long-range duels, where the side that could see and hit first from the greatest distance would win. And on paper, the missile tank seemed like the ultimate weapon for this new kind of war. The theoretical advantages were undeniable. A conventional tank gun in the 1960s had an effective range of perhaps 1,500 to 2,000 meters. Beyond that, accuracy dropped off sharply. A guided missile, however, could fly straight and true for 4 kilometers or more. It didn't lose velocity or penetrating power over distance. Whether the target was 500 meters away or 4,000 meters away, the missile would hit with the same devastating force. Precision was another key selling point. A kinetic round is a dumb projectile. Once it leaves the barrel, it follows a ballistic arc. Wind, humidity, barrel wear, all these factors can cause a miss. A guided missile, by contrast, is smart. The gunner can steer it onto the target, correcting its flight path in real time. If the enemy tank moves, the missile can follow. And then there was penetration. To punch through modern armor with a conventional shell, you needed a massive gun, firing a heavy, high-velocity round. This required a large, heavy tank to absorb the recoil. A missile carries its own warhead. It doesn't rely on the speed of the launch to penetrate armor. It relies on the explosive charge it carries. This meant a small, light vehicle like Object 775 could carry a weapon capable of destroying the heaviest tanks in the world. But there was a critical oversight in this thinking. War is not fought on paper. It is fought in mud, dust, smoke, and chaos. And in the chaotic reality of the battlefield, the theoretical perfection of the missile began to fall apart. First, consider the environment. A guided missile requires continuous line of sight. The gunner must track the target from the moment of launch until impact. This might take 10 or 15 seconds for a long-range shot. In combat, 10 seconds is an eternity. When a tank fires, it kicks up dust. Explosions throw debris into the air. Smoke screens are deployed. If the gunner loses sight of the target for even a second, the missile misses. A conventional round, traveling at supersonic speed, reaches its target almost instantly. It doesn't care about smoke or dust once it's in the air. Second, consider the vulnerability of the guidance system. The missiles used by Object 775 relied on radio commands or wire guidance. These systems were delicate. Electronic interference, shock waves from nearby explosions, or even the vibration of the tank itself could disrupt the signal. A conventional shell has no electronics to fail. It is a solid piece of metal. But the most profound flaw was doctrinal. A tank is not just an anti-tank weapon. It is a multi-role combat system. It needs to support infantry, destroy bunkers, fight in cities, and hold ground. A conventional tank carries a mix of ammunition, armor-piercing rounds for other tanks, high explosive rounds for infantry and buildings, and smoke rounds for concealment. Object 775 was optimized almost exclusively for killing other tanks at long range. Its missiles were expensive and scarce. Using a guided missile to blow up a machine gun nest or a truck was a waste of resources. Furthermore, the missile system had a minimum range. The missile needed time to stabilize after launch, and for the guidance system to capture it. This created a dead zone of several hundred meters around the tank where it could not effectively engage targets. In the close quarters fighting of an urban environment or a dense forest, Object 775 would be helpless against enemy tanks or infantry armed with RPGs. This specialization reduced the tank's flexibility. In the industrial-scale warfare the Soviet Union was preparing for, versatility is often more valuable than perfection. A tank that can do 5 jobs adequately is better than a tank that can do 1 job perfectly but fails at the other 4. By designing a machine that was purely an anti-tank sniper, the Soviets had created a weapon with a very narrow utility. It was excellent at killing tanks at 4 kilometers on a clear day on a flat plain. But in the messy, unpredictable reality of war, those ideal conditions are rare. Object 775 was a one-trick pony in a circus that demanded a variety of acts. And as the engineers pushed the boundaries of technology to make their missile tank work, they were inadvertently designing a machine that was too fragile, too complex, and too specialized to survive the brutal test of combat. To achieve the radical capabilities of Object 775, the Soviet engineers had to make a series of extreme engineering decisions. Perhaps the most controversial was reducing the crew to just 2 men. Traditionally, a tank crew consisted of 3 or 4 soldiers, a commander, a gunner, a loader, and a driver. Each man had a specific role. The loader fed the gun, the gunner aimed and fired, the driver maneuvered the vehicle, the commander coordinated everything and communicated with other tanks. Object 775 eliminated the loader entirely, replacing him with an automatic loading mechanism for the missiles. This was a logical step for a missile tank. But then, the designers went further. They combined the roles of the gunner and the commander into a single person. This decision had profound consequences. By removing 2 crew members, the designers could make the tank much smaller and lighter. The internal volume required for the crew was drastically reduced, allowing for a lower silhouette and thicker armor relative to the vehicle's weight. However, this efficiency came at a cost. The workload on the remaining crew members increased dramatically. The commander now had to command the tank, search for targets, communicate on the radio, and operate the complex missile guidance system. In the heat of battle, this cognitive load could be overwhelming. From a systems perspective, reducing the crew increased the risk of single-point failure. In a 4-man tank, if one crew member is injured or killed, the others can often take over his duties to keep the tank fighting. In a 2-man tank, the loss of either crew member effectively cripples the vehicle. If the commander is incapacitated, the tank cannot fight. If the driver is hit, the tank cannot move. The redundancy of a larger crew was sacrificed for compactness. But the most bizarre engineering feat was the turret itself. In a standard tank, the driver sits in the hull, looking forward through periscopes. The turret rotates above him. In Object 775, the driver was moved into the turret alongside the commander. This created a unique problem. If the driver is in the turret and the turret rotates, the driver rotates with it. When the gun points to the right, the driver is looking to the right. This would make driving impossible. Imagine trying to steer a car while looking out the side window. To solve this, the engineers designed a turret within a turret. The driver sat in a small, independently rotating capsule inside the main turret. This capsule was mechanically linked to the turret's rotation gear, but in reverse. As the main turret turned clockwise to aim the gun, the driver's capsule turned counterclockwise at the exact same speed. The result was that the driver always remained facing the front of the tank hull, regardless of where the turret was pointing. It was a brilliant, dizzying solution to a problem created by the desire for extreme compactness. This system required incredible precision. The gears had to be perfectly synchronized. The mechanical linkages had to be robust enough to withstand the shock of firing and cross-country movement, yet delicate enough to maintain alignment. Continuous calibration was essential. If the synchronization slipped even slightly, the driver would become disoriented. He might think he was driving straight when he was actually turning, or vice versa. In the dust and vibration of a battlefield, maintaining this complex mechanism would be a nightmare for maintenance crews. It was mechanically ingenious, a testament to Soviet engineering prowess, but it was also operationally fragile. Complexity is the enemy of reliability in combat. A system with more moving parts is a system with more ways to fail. The final piece of extreme engineering was the suspension. Object 775 used a hydropneumatic suspension system, similar to the one used on the famous Citroën cars, but adapted for a 36-ton tank. This system allowed the driver to adjust the ground clearance of the tank. By pumping hydraulic fluid into the suspension cylinders, the tank could rise up to clear obstacles. By releasing fluid, it could squat down, reducing its already low profile even further. This capability was tactically revolutionary. The tank could kneel behind a ridgeline or in tall grass, exposing only the very top of its turret, just enough to launch a missile. It could tilt its hull forward or backward to increase the elevation or depression of the launcher, giving it better angles of fire in hilly terrain. However, like the counter-rotating turret, the hydropneumatic suspension introduced a new layer of complexity. Hydraulic systems operate under high pressure. Seals can leak. Lines can burst. Fluid can become contaminated with dirt or water. In a civilian car on a smooth road, hydropneumatic suspension provides a smooth ride. In a tank slamming over rocks and through mud, it is a constant maintenance headache. A conventional torsion bar suspension is simple, rugged, and easy to fix in the field. A complex hydraulic system requires specialized tools, clean fluids, and trained technicians, resources that are often scarce on the front lines. The engineers had built a machine that could do amazing things. It could squat, spin its insides, and fire missiles with deadly accuracy. But in doing so, they had created a machine that demanded a level of care and precision that the harsh reality of war rarely permits. The heart of Object 775 was not its engine or its armor, but the Rubin missile complex. This was a sophisticated system designed to fire the 9M15 Typhoon anti-tank guided missile. The missile itself was a formidable weapon, 125 millimeters in diameter, 1.5 meters long, and capable of penetrating 500 millimeters of steel armor at a range of 4 kilometers. The control equipment for this system was massive. It occupied 200 cubic decimeters of space inside the cramped turret and weighed 180 kilograms. In the early 1960s, electronics were still in their infancy. Transistors were replacing vacuum tubes, but integrated circuits were rare and expensive. The guidance computer for the Rubin complex was a bulky, heat-generating box filled with delicate components. Technological constraints were severe. The electronics had to withstand the shock of firing a missile, the vibration of a tank moving cross-country, and the extreme temperatures of a battlefield. Reliability was a major concern. The mean time between failures, MTBF, for early solid-state electronics was notoriously low. A loose connection or a fried transistor could render the entire weapon system useless. The concept required a level of miniaturization and ruggedness that the Soviet industrial base was struggling to provide. The engineers were essentially trying to build a 1980s-style fire control system using 1960s technology. It was an ambitious reach, but perhaps a bridge too far. Despite the immense technical challenges, Object 775 was built and tested. On the proving grounds, it demonstrated some remarkable capabilities. Powered by a 700 horsepower 5 TDF diesel engine, the same compact, opposed piston engine used in the revolutionary T-64 tank, it was fast and agile. It could reach speeds of around 70 kilometers per hour on roads, making it one of the fastest armored vehicles of its time. Its extremely low profile and hydropneumatic suspension gave it excellent mobility on soft terrain. It could traverse marshes and deep snow that would bog down heavier tanks. In tactical exercises, it proved difficult to spot visually and even harder to hit. Its ability to kneel behind cover made it a master of ambush. On mobility metrics alone, Object 775 was a success. It was lighter, faster, and stealthier than the T-62S it was intended to replace. But a tank is more than just a fast tractor. It is a fighting machine. And when it came to fighting, the cracks in the design began to show. The first major problem was visibility. The extremely low silhouette, which was the tank's greatest defensive asset, turned out to be its biggest liability for situational awareness. The crew sat so low in the hull that their view of the battlefield was severely restricted. In tall grass or undulating terrain, the commander could barely see over the top of the vegetation. In armored warfare, spotting the enemy first is critical. Survivability equals detection speed plus reaction time. If you can't see the enemy, you can't shoot him. And if you can't see the terrain, you can't maneuver effectively. The low height of Object 775 blinded its crew, forcing them to rely heavily on periscopes and electronic sensors that were often inadequate. The missile system itself proved unreliable. During testing, the 9 M15 missiles suffered from a malfunction rate of approximately 30 to 40. Guidance signals were frequently lost mid-flight, causing missiles to veer off course or crash into the ground. Launch failures were common, leaving the tank defenseless with a live missile stuck in the tube. For a specialized missile tank, unreliable missiles are fatal to the mission identity. A conventional tank can fire shell after shell until it hits. A missile tank carries a limited number of expensive, complex rounds. If a third of them fail, the tank becomes a liability. The promise of one-shot, one-kill precision evaporated in the face of technical reality. Finally, the maintenance burden was overwhelming. The complex synchronization mechanisms for the counter-rotating driver's capsule required constant adjustment. The sensitive electronics of the Rubin guidance system were prone to failure from vibration and dust. The hydropneumatic suspension leaked and jammed. The Soviet army relied on conscript soldiers with limited technical training. They needed equipment that was rugged, simple, and easy to fix in the field with basic tools. Object 775 required a team of highly trained technicians with specialized equipment just to keep it running. It was a Formula One car in a demolition derby. Brilliant, but fragile. The field tests revealed a harsh truth. Object 775 was a technological marvel, but a practical failure. It was too complex, too specialized, and too unreliable for the brutal realities of mass armored warfare. The dream of the missile tank was colliding head-on with the laws of physics and logistics. The failure of Object 775 to perform reliably in field tests was a wake-up call for the Soviet military-industrial complex. The dream of a pure missile tank, a machine that would render the gun obsolete, was proving to be a technological dead end, at least for the time being. But the desire to integrate guided missiles into armored warfare didn't disappear. It just evolved. Instead of pursuing a radical redesign that threw out the baby with the bathwater, Soviet engineers pivoted to a more pragmatic approach. They asked a different question. Why replace the gun when you can just make the gun smarter? The answer came in the form of the T-64B. This was not a missile tank. It was a main battle tank that could fire missiles. The engineers developed a system called Cobra, a T-8 songster, which allowed a 125mm guided missile to be launched through the same smoothbore barrel used for conventional shells. This was a brilliant compromise. It retained all the advantages of a traditional tank. The T-64B still had a crew of 3, a familiar layout, and the ability to fire high-explosive and armor-piercing rounds for close-range combat and infantry support. But with the push of a button, it could switch to a guided missile mode, extending its lethal reach to 4 kilometers. This modular innovation solved the problems that had doomed Object 775. The tank was no longer helpless if the missile system failed. It could still fight with its main gun. The crew wasn't overwhelmed by a 2-man workload. The logistics were simpler because the tank used standard parts and ammunition. And most importantly, the cost was manageable. The T-64B represented incremental innovation. It took a proven platform and added a new capability rather than trying to invent a whole new platform from scratch. In the world of military procurement, where reliability and cost are king, incremental innovation almost always wins over revolutionary transformation. Object 775 was a revolution that failed. The T-64B was an evolution that succeeded. So why did Object 775 fail so spectacularly? Was it just a bad idea? A systems-level analysis suggests that it wasn't a bad idea, but a misaligned one. The project suffered from several structural failures. First, there was a technology maturity gap. The electronics required to make a 2-man, missile-only tank work simply didn't exist in 1964. The guidance computers were too big, too hot, and too unreliable. The sensors needed to give a 2-man crew situational awareness were primitive. The engineers were trying to build a digital tank in an analog world. Second, there was an over-optimization of height. The obsession with making the tank as low as possible compromised everything else. It forced the crew into a cramped, complex turret. It limited visibility. It made the suspension overly complicated. In their quest for the perfect ambush predator, the designers forgot that a tank also needs to see, move, and fight in a variety of conditions. Third, there was an underestimation of battlefield chaos. The designers assumed a clean, orderly war, where tanks would engage each other at long range like snipers. They didn't account for the dust, smoke, and confusion that make guided missiles difficult to use. They didn't account for the need to support infantry or fight in cities. They built a machine for a war that existed only in theory. Finally, there was the issue of cost and complexity. A tank that costs 3 times as much as a T-62 and requires a team of scientists to maintain is not a viable weapon for a mass army. The Soviet Union needed thousands of tanks that could be operated by conscripts and repaired in the field. Object 775 was a boutique weapon for an army that bought in bulk. It is easy to look back at Object 775 and see a failure. But in the context of innovation, failure is often just a stepping stone. The lessons learned from this strange, flattened tank would go on to influence Soviet armor design for decades. It proved that guided missiles could be effective tank killers. It showed that autoloaders were viable. And it demonstrated the limits of how far you can push a design before it breaks. History is often a matter of timing. Object 775 was a failure in 1964. But what if it had been built 20 years later? By the 1980s, the technological landscape had shifted dramatically. The bulky vacuum tubes and primitive transistors had been replaced by microprocessors. Digital fire control systems were becoming standard. Thermal imaging sights allowed tanks to see through smoke and darkness. If Object 775 had been designed in this era, many of its fatal flaws might have been solvable. The complex analog guidance computer for the missiles could have been replaced by a compact digital unit. The situational awareness issues caused by the low silhouette could have been mitigated with remote cameras and sensors. The reliability of the missiles themselves would have improved significantly with solid-state electronics. In fact, if you look at modern tank concepts today, they often resemble Object 775. We see unmanned turrets, crews located deep within the hull for protection, and heavy reliance on guided munitions. The idea of a missile tank with a two-man crew is not dead, it was just sleeping. Vehicles like the Russian T-14 Armata or various Western prototypes explore similar configurations: automated loading, remote weaponry, and advanced sensors to reduce crew size. In that sense, Object 775 was a prophet. It anticipated the direction of armored warfare long before the technology was ready to support it. It was a vision of the future, trapped in the hardware of the past. Although the project was canceled in 1968, Object 775 left a lasting legacy. The experience of trying to integrate guided missiles into a tank turret was invaluable. The Soviet engineers learned how to handle the delicate electronics, how to manage the launch sequence, and how to stabilize the guidance beam. These lessons directly influenced the development of the gun-launched missile systems used on the T-64, T-72, and T-80 tanks. The obsession with low silhouette also persisted. Soviet tanks remained significantly lower and smaller than their NATO counterparts throughout the Cold War. While they never went as extreme as Object 775, the principle of smaller target equals better survival became a core tenet of Soviet design philosophy. Perhaps most importantly, Object 775 served as a cautionary tale about automation. It demonstrated that removing crew members increases the workload on those who remain. This insight led to a more balanced approach in later designs, where automation was used to assist the crew rather than replace them entirely. The Soviets stuck with three-man crews for their main battle tanks, recognizing that a human loader might be replaceable, but a human brain is not. It also confirmed that versatility beats specialization. The failure of a pure missile tank reinforced the value of the main gun. A tank needs to be able to fire cheap, reliable, high-explosive shells at infantry, bunkers, and light vehicles. It needs to be a multi-tool, not a scalpel. This philosophy guided Soviet armor development for the next 30 years. Object 775 embodies radical innovation. It was a bold attempt to rethink the fundamental nature of the tank. It challenged every assumption: the gun, the turret, the crew, the height. It was a machine born of pure engineering ambition. In contrast, the T-64B represents evolutionary innovation. It took an existing platform and made it better. It didn't try to change the world, it just tried to survive in it. Military history repeatedly shows that systems balancing innovation with practicality survive. The Spitfire, the T-34, the M1 Abrams, these were innovative, but they were also practical. They could be built, maintained, and fought with. Systems that pushed too far beyond technological readiness, like the Me-163 Comet or the Zumwalt-class destroyer, often collapse under their own complexity. Object 775 was not a failure of imagination. If anything, it had too much imagination. It was a failure of timing. The engineers saw a future where missiles ruled the battlefield, where tanks were low-profile stealth machines, and where automation replaced muscle. They were right about the future. They were just wrong about when it would arrive. And in strategic development, timing is often more decisive than brilliance. Being right too early is indistinguishable from being wrong. Object 775 sits today in a museum, a strange, flat curiosity. But it is a monument to the restless spirit of innovation that drives military technology. A reminder that sometimes the path to the tank of tomorrow is paved with the failed prototypes of yesterday. History has a tendency to remember the winners, the machines that worked, the tactics that succeeded, the generals who triumphed. But the graveyards of military engineering are filled with brilliant failures like Object 775. These machines are not mistakes. They are questions asked in steel. Object 775 asked, "What if a tank could hide in plain sight?" It asked, "What if we don't need a gun?" It asked, "What if 2 men are enough?" The answers it received from the battlefield were harsh, but they were necessary. Without the failure of Object 775, we might not have the sophisticated guided munitions of today. We might not understand the limits of automation. We might still be chasing the dream of the perfect, invisible tank. There is a quiet dignity in this strange, flattened machine. It represents the courage to be wrong, to push technology until it breaks, just to see where the breaking point is. In a world that often rewards safe, incremental progress, Object 775 stands as a testament to the radical spirit of innovation, even if that spirit sometimes leads to a dead end. Thank you for spending part of your day with us to uncover this hidden chapter of Cold War history. If this story of ambition and engineering resonated with you, we'd be honored to have you with us again.